Morning students. In today's lecture, we will discuss the phase diagrams of one component systems. Before that, we must know what are the phase diagrams and what information we get from the phase diagrams. We very well know the number of phases that exist together in a heterogeneous system. When the system is in equilibrium, that all depends upon the conditions of temperature, pressure and composition. Now phase diagram is what? It is a plot which gives us the conditions of equilibria between various phases of a given system. Means under what condition, how many type of phases will be in equilibrium and which type of phases will be in equilibrium. These diagrams will contain a number of lines, areas and triple points, which we all discuss in detail in its slides. So first we are discussing the phase diagram of one component systems. Now according to Gibbs phase rule, we very well know the number of degrees of freedom is equal to number of components minus number of phase plus 2. Now in case of one component system, different cases may arise. First one is when there is only one phase present. In that case, P will be equal to 1. Now as it is for one component system, so value of C is also equal to 1. So we can get the value of F is equal to 1 minus 1 plus 2, that is 2. So the system is bivariant in case of a one component system when we are talking about the one phase. So a single phase in a one component system phase diagram will be represented by an area. When we will plot pressure versus temperature, the single phase in a one component system phase diagram will be represented by an area. As the system is bivariant, there are 2 degrees of freedom. Now when there are 2 phases in equilibrium, in that case P will be equal to 2. So F comes out to be 1 minus 2 plus 2 and that comes out to be F equal to 1 minus 2 plus 2 equal to 1. So when there are 2 phases in equilibrium, we are getting degrees of freedom equal to 1. So the system is monovariant and will be represented by a line on pressure temperature graph, or you can say phase diagram of one component system. When there are 2 phases in equilibrium, the system will be monovariant and it will be represented by a line. As in this case, the number of degrees of freedom is 1. Next one, when there are 3 phases in equilibrium, in that case total number of degrees of freedom comes out to be 0. So we can't variate any out of pressure and temperature independently. When the degrees of freedom is 0, there is no independent variation of any variable. There is a fixed value of temperature and pressure. We will get all the phases in equilibrium. So the system is invariant or non-variant, and it will be depicted by a single point on the pressure temperature graph, and we also term it as triple point. At this point, all the 3 phases, solid, liquid and vapor, will be in equilibrium. Now, we will exemplify it with the water system, which is very important system. So, how we can discuss in water system? Under normal condition, the water exists in 3 phases, namely liquid water, ice and water vapor. There are different 3 phases of the water. It can exist as solid, liquid and vapor. All these phases can be represented by only a single constituent, which is the water. That's why it is a one component system. We can express the composition of each phase only in terms of water. That's why it is a one component system. Now this is the phase diagram of water system. As we can see in the phase diagram, there are different lines and points and areas in this water system phase diagram. So we can see here the curve OA. The curve OA is representing here the vapor pressure curve, which is showing the equilibrium between water and water vapor. Along this curve, there are 2 phases in equilibrium. These are water and water vapor. If we talk about the areas, first we talk about the areas. In this area, we are having only ice, or you can say solid water. In this area we are having only vapors, and in this area we are having only water. So ice, water and vapor are existing in these three areas. So along this line, which is a vapor pressure curve of water, we are having water and vapor in equilibrium with each other. In this line, along this line OB, which is a sublimation curve, along this line ice and water vapor, they will be in equilibrium with each other. And we talk about the OC line. The OC line is the fusion curve. Along this line, two phases in equilibrium will be ice and water. And O is the point which is known as the triple point. At this point, all the three phases will be in equilibrium: ice, water and water vapor. The conditions are mentioned here. At the triple point, we are having 0.0098 degrees Celsius temperature and pressure equal to 4.58 mm. So this is all about the general discussion of the phase diagram. We will discuss each and every point in details in the next slides. So the system is consisting of three phases, and different type of equilibria can exist in the water system. That may be either liquid and vapor, solid and vapor, solid and liquid, and all solid and liquid and vapor are in equilibrium. So different type of equilibrium are in phase diagram of water system. So first, the phase diagram of water consists of three stable curves: OA, OB and OC. OA, OB and OC, and one metastable curve which is OA dash. And there are three areas. These three areas are here, which we have discussed already, and one definite point O, which is also known as a triple point. Now curve OA, the vapor pressure curve of water. This is the curve OA, which is the vapor pressure curve of water. It represents the equilibrium between liquid water and water vapor at different temperatures and is known as vapor pressure curve. Above this curve, the liquid water alone exists, and below it only water vapor exists. Above this we are having only water, and below this only water vapor. At any point on this curve, the two phases water liquid and water vapor, they exist in equilibrium. Now O is the freezing point of water and A is the critical point. O is the freezing point of water. We can see here below this the water is existing as ice. So O is the freezing point of water and A is the critical temperature above which there is no liquid is existing at any pressure. Above the critical temperature, the water is existing only in the form of vapor. So A is the critical point corresponding to temperature 374 degrees Celsius and pressure 218 atmosphere. Pressure 218 atmosphere and temperature 374 degrees Celsius. Now applying the Gibbs phase rule, F is equal to C minus P plus 2, C is equal to 1, and number of phases they are existing 2 along this curve. So we are getting F is equal to 1. So system is univariant along this line. For a particular value of temperature, we are having a definite value of pressure. We can only independently vary one of the variable out of pressure and temperature. So the system is univariant. Now what about the slope of curve? Slope of curve we can get from the Clausius-Clapeyron equation, according to which dP by dt is equal to del Hv by T into molar volume of vapor minus molar volume of liquid. Now we can see the molar latent heat of vaporization, that is always positive. Now molar volume of vapor will be always greater than the molar volume of liquid. So denominator we are also getting the positive term. So dP by dt will be positive, which suggests that the slope of curve OA will be positive. That's why we are getting here the positive slope of the curve OA. So this is all that discussed here, that del Hv is the molar latent heat of vaporization, Vg is the molar volume of water vapor, Vg means Vv here, and Vl is the molar volume of water. Now what about curve OA dash, which is the metastable vapor pressure curve for supercooled water. Metastable vapor pressure curve for supercooled water. Now how we are getting this curve OA dash? This OA dash curve is obtained by continuing this vapor pressure curve of normal water and vapor. When the vapor pressure curve of normal water is continued on the left hand side of O, we are getting a curve which is known as metastable curve of supercooled water. By very carefully cooling this normal water below the point O, we are getting supercooled water state, which is representing by OA dash. Supercooled water means without getting ice, we are simply cooling the water below the 0 degrees Celsius. So this is obtained by very careful change of conditions. If we will little disturb the system, immediately supercooled water will be converting to ice and this curve will merge into OB curve. So curve OA dash lie above the curve OB. Consequently, the vapor pressure of the metastable system is higher that of the stable system curve OB at the same temperature. As the curve OA dash is lying above the curve OB, at any temperature, the vapor pressure of the supercooled water is higher than that of ice. There is no break in the vapor pressure curve as the solid phase doesn't separate in case of supercooled water, and on slight disturbance this supercooled water will at once change to the solid ice and merge into the OB. Now next is the curve OB, the sublimation curve of ice, which represent the equilibrium between ice and vapor at various temperatures and pressures. Curve OB. This is representing the equilibrium between ice and vapor at various temperatures. Curve OB, as per the Clausius-Clapeyron equation, dP by dt, that is equal to del H of sublimation divided by T into molar volume of vapor minus molar volume of solid. Again, the enthalpy of sublimation is always positive. So this is positive, and molar volume of vapor is always greater than molar volume of solid. So denominator is also positive. So the slope of the curve OB will always be positive in case of water system. So the OB curve is having a positive slope, as we can see from the figure. Like OA, it is also having a positive slope. Positive slope indicates that the vapor pressure of ice increases with temperature. Positive slope means the vapor pressure is increasing with temperature. As the temperature is increasing, pressure is also increasing in this curve. The next one is the curve OC, the melting point curve of ice. Curve OC represents the equilibrium between ice and liquid at different temperatures. Along this curve we are having ice and liquid. Here is ice and here is the liquid water. These both are in equilibrium along the curve OC. Now one main important point regarding OC is that it is having a negative slope. As we can see from the figure, it is having a negative slope. It means melting point of ice that is decreasing with increase in pressure. As we can see from the figure, the melting point of ice that is decreasing with increase in pressure. We will discuss in detail. The curve OC is inclined towards the pressure axis. The slope of curve OC is negative, which indicates that melting point of ice is lowered by increase of pressure. Now how it is negative? We can find out it from the Clausius-Clapeyron equation. Clausius-Clapeyron equation suggests that dP by dt is equal to del HF, molar latent heat of fusion, divide by temperature into molar volume of liquid minus molar volume of solid, as there is equilibrium between solid and liquid here. Now in this case we very well know the density of ice is less than that of water. This is a unique property of water, that density of ice is less than that of the water. Now if density is less, for the same mass of water, molar volume of solid will be greater than that of the molar volume of liquid, as density is inversely proportional to volume. Density is given by mass by volume. So if density is less, then volume will be higher. So it means the molar volume of ice will be higher than that of molar volume of water. So we can say Vs will be higher than Vl. So it means the denominator is having a negative term. So ultimately dP by dt will be negative. So the slope of curve OC will be negative. Now further we can see there is no upper limit for the curve OC in the phase diagram. It goes up to 2240 atmosphere and minus 22 degrees Celsius. As we can see, the curve OC that is inclined towards pressure axis, it is not having any upper limit. above 2240 atmosphere and minus 22 degrees Celsius, the ice will be converted into the different forms, which we will discuss in the high pressure phase diagram of water. Now at this point, one type of ice is changing into another structural form. So that will be all discussed in the later on in the phase diagrams. At any point on the curve OC, the two phases which are in equilibrium are ice and liquid water. And the system will be again univariant, as in case of other lines. Along this line also the system will be monovariant or univariant. Now what about areas and triple point? Area AOC, AOB and BOC. Area AOC is representing the single phase liquid water. Area BOC is representing the single phase ice, and area AOB is representing the single phase water vapor. We have already seen this in the diagrams about all the areas. AOC water, AOB that is water vapor, BOC that is representing ice. Now what about triple point? At triple point all the three phases are existing together. So the single point indicating here that three phases exist only under one set of conditions corresponding to temperature equal to 0.0098 degrees Celsius and pressure equal to 4.58 mm. So there is only single condition is there at which all the three phases can exist together. If we will little change out of any of these two, temperature or pressure, then any one of the phase will disappear. So the system is non-variant at triple point O. We can't independently vary any one of temperature or pressure at triple point O. Similarly, in case of areas, the system will be bivariant. Each area is represented by 2 degrees of freedom. We can independently vary both the pressure and temperature in the areas. So single phase is represented by area, and triple point the system is non-variant, and system at point A is invariant or non-variant. So this is all about the summary of important parts of the phase diagram of water system. We have already discussed each. Now next is the effect of change of temperature at constant pressure on water system. So when we are varying the temperature at constant pressure, what is happening? So consider the effect of temperature on water system at a constant pressure of 1 atmosphere. We have kept the pressure at 1 atmosphere constant. Now we are observing the effect of temperature. Suppose we are starting point from the point A, where water existing as ice at a temperature much lower than 0 degrees Celsius. Heating slowly along the path ABCD as we are increasing the temperature. On reaching at point A, the system is bivariant. On reaching point B, melting of ice will start. Now temperature will remain constant till whole of the ice is melted. On further heating along path BC, the temperature of liquid water will rise up to the point C. Along BC, the system is existing in the form of only water. At point C, the temperature is remaining constant till whole of the water is converting to vapor. Beyond point C, the heat supplied raises the temperature of vapor along the path CD. So this is the effect of change of temperature at constant pressure on water system. Now next one is high pressure phase diagram of water system. Now we have already discussed that melting point of ice decreases with increase of pressure. There is negative slope of melting point curve of ice when there is ice and water are in equilibrium. Now after the pressure above this pressure, when 2240 atmosphere pressure is crossed, what you will see, on further increasing pressure, different forms of ice are formed. Ice converts from one form into another form, and these forms differ in density, crystal structure as well as other physical properties. The form of ice at 2240 atmosphere and minus 22 degrees Celsius is the ordinary ice, and it is called as ice 1. On further increasing the pressure, different forms of ice are formed: ice 2, ice 3, ice 4, 5, 6 and 7, so on. Now melting point of these forms you will see. Further on increasing the pressure, the melting point of these forms is increasing with increasing the pressure. Now the variation is opposite. Below this pressure, the melting point was decreasing with pressure. Above this pressure, for the different forms of ice, the melting point is increasing with increasing pressure. And for ice 7, you will see the melting point is reaching to the temperature nearly 100 degrees Celsius at a pressure of 25,000 atmosphere. So we can see here how hot is the melting of ice at 25,000 atmosphere. It is reaching up to 100 degrees Celsius, which is the boiling point of water. So this is all about the high pressure phase diagram of water system when the ice is converting into the different forms and melting point of ice is increasing with increasing pressure. In the next chapter, we will continue in the next system. Thank you.